This is work done at Robotics at Google and in collaboration with Everyday Robots. So the prompt for this talk is, what do you think is the biggest bottleneck that prevents solving robot learning today? Any suggestions? Yeah.
Collecting data in the real world.
Yes.
I went to a talk where they posited still robotics, like the ability to manipulate things well. Right? It's like kind of aligned with manipulations to certain like intents.
Can you repeat that again?
So basically, they posited that it's actually the robot. They're like robots still have the problem. So it's like robots aren't deft enough and cannot like align well enough to certain intents.
That's correct. Yeah.
Distribution shift.
Distribution shift. Correct. Yeah, so one of the setups that, or one of the problem setups that we see robots today is that they are very generalized. They are not anymore in operating in industrial environments where they are very constrained. So in generalized setups, the interaction with robots or the tasks that are asked of them is usually in language. So we are building something that operates in a home or office environment. And so the prompts look like this. I spilled my drink, can you help? Or I just worked out, can you bring me a snack and a drink to recover? Or I'm feeling tired, can you make me a latte? Now, as the gentleman here pointed out, data collection is really hard. And we know that because we have tried it. And the problem is that it requires a lot of like engineering heavy operation in order to collect the required data for manipulation. And earlier we were doing it with a fleet of robots with like fixed base. And it takes a ton of time to learn even a smaller skill. Now the question to satisfy any of the prompts that I showed in the last slide, you need to have a mobile manipulator. So it needs to go around. It can't just like stay in a position. It needs to go around and collect its data. And the type of problems are both navigation and manipulation. And you also have a bunch of like planning related problems coming into the picture. Now, does this remind you of like a trend that we have seen in recent research? The idea is that because data collection is very hard, we need to attach ourselves to an existing trend that would collect data for us that would collect data for us automatically. And this sounds very similar to Richard Sutton's The Bitter Lesson. So Richard Sutton claimed that one of the biggest breakthroughs in AI research has been the fact that computation has become cheap over the last 70 years. And for a long time, scientists were distilling human knowledge into engineering-based approaches to solve AI problems. But ultimately, what worked was something very simple, something that was composable, and something that could scale with computation. So what we learned from the bitter lesson is that AI will need a lot of computation, and computation is getting cheaper. And it is important that any work on AI problems would leverage on that trend. Now, given where we are, and this has led to like a revolution in computer vision, in natural language processing, in search-based learning for like chess or Go. Now, given where we are, is there a bitter lesson waiting for us in robotics? And if so, what could it be? Suggestions? Anyone? Okay, I'll go ahead. So, like you pointed out, robotics will need a lot of data, and robotics will need to understand the world and model the world through data itself. So then the question is there a trend that is generating a lot of data and that whose efficiency is growing is already improving in research by use of a lot of data? And we need to attach work on robot learning with that trend. Any ideas for trends in robotics right now, or trends in research that we could use in robotics? Language models. Yeah. Yeah, I guess I gave that away with the title of the talk. Yeah, language models. So over the last decade, language models have gotten really, really good. So with BERT, GPT-2, GPT-3, and while they are trained only on next token prediction, they have become extremely smart in understanding very general trends in data. They encode like a wealth of human knowledge, and you see the emergent behavior of them quite understanding the world and also beginning to reason about it. And so, yeah, foundation models are the new trend. And the properties are that of foundation models is that there's a lot of interest among them. They scale very well with data and compute. And they also get they're also getting better at understanding the world. So the idea is that because the beta lessons told us that we need to leverage compute in order to make progress in AI. And the next beta lesson might be that we actually need to leverage foundation models to make leaps in robotics. Now, just to give an overview of the language models or language-based foundation models out there, language has almost become like the universal interface to which we are interfacing with AI. So there is Imagen, there is Palm. Imagen does like image generation using text prompts. Then there is also DeepMind's Flamingo. There is visual language models, translation, all sorts of things. So language has established itself as a very natural interface. Language encodes a wealth of knowledge about our world that can be easily leveraged. So now the question is, how can we exactly apply foundation models in robot learning? And I'll hand over to my colleague Yao to explain how we use this at Robotics at Google.
Yeah, thank you, Keerthana. So yeah, the question is, how do we kind of develop robot learning methods that could scale with better foundation models? So yeah, let's see. So over the years, actually, in our kind of team, we have built a lot of, on the right side, you can see like we have built a lot of kind of robot learning models from doesn't work at all in the real world to it works for some like simple tasks, all the way to it can actually work on multiple different tasks. However, there are still a lot of constraints. For example, I mean, even if it works on multiple tasks, as Keerthana said, it's like a fixed base. It's just like one arm only with a gripper. And also like for the task representation, it's not like the language or whatever that it can actually understand, but it's kind of very simple like task IDs. Use like task number 1 for one task and task number 2 to represent the other task, etc. So we are trying to see that how can we try to make a link between the language model to the robot learning stuff that we have been doing so far. And if you look at the language, it actually has a lot of kind of good properties. That's why we choose the language to start. So for example, the language is actually a very efficient task representation in a way that it's actually, you just put like a simple sentence, right? And then it can represent task. If you think about it, some other ways to represent task, it could be like, you can use a few kind of images to represent this task. For example, stick the blocks on top of each other. You can have like an initial image, something in the middle, and something final. Or you can even have like a video. But as you know, like all those kind of data, like image and video data are very large. But here the language is only a few kind of words, and then you kind of know exactly what it means. And then like it's also interpretable, meaning that if you're given like a high-level task, and then the language model is actually capable of trying to decompose the whole long-range task into like smaller ones, so that it could be kind of solved like using simpler robotics primitives. And then like it's also compositional in a way that, for example, if you teach the robot to like pick an apple, or you teach the robot to like move an orange near a bottle, and then it's easily composed in a way that robot learn to do like pick a bottle in a very easy way, so that you can kind of make your kind of data collection more efficient. And it's also very accessible. Like we try to ask human to, do some demonstration and teach the robot what kind of like the way to solve a task. And you can also want the robot to communicate with a human. For example, if he knows something the robot cannot do, the robot can just say that I cannot do it, things like that. And then it's a very natural kind of way to communicate between like human and the robot. And finally, it's also very abundant in a way that there are currently a bunch of different kinds of large models like VRMs and LMs, or like audio language models. And all those kind of things, they use language as an API to kind of connect them together. So the language is actually at the center of all those kind of large models. And then, like, how do we actually use language in the robotics? So let's actually first take a look at how the traditional planner works in the robotics kind of area. So let's say if this is a scenario, you have a robot has a banana and there's like a drawer, and just like task ask you to, for example, ask the robot, for example, to bring me a snack. The traditional kind of planner will try to think about how to actually achieve this task. For example, at the end of the day, you need to kind of close the top drawer, and then you will also need to hand over something to the user. For example, you hand over a planner or like some chip bags, right? And then the input to the planner are basically some word states as well as the robot state. Word state is like what the robot observes outside. The robot state is something internally for the robot. The word state could be something like if you have a camera, you can have show the camera image, and also you may have like a 2D map of the surroundings. The internal robot states could be like the joint angles, or like the positions of the arm, or like the closeness of the gripper, all those kind of things that describe the internal states. So given all those kind of states and the task, the planner will try to come up with a policy, and the policy, according to each of the timestamps, there's some input to the policy to decide the action. So that's how the traditional planner works. So how does the language planner work in this way is that you can just basically replace the traditional planner into a large language model planner. And then like the task says like, bring me a snack. It will be just such a string called bring me a snack. And then all the word states could be also, interpreted in the language way. And also the robot state is also something could be described using the language directly. And all those kind of things could be fed into the language model, and then it will come up with a policy and decide the actions. Then let's look at what kind of language model could we kind of use. There are actually multiple different teams in the Google who are working on language models. PaLM is one of the team which actually trained a very, very large, actually this is like the largest language model in the world right now, much larger than like GPT-3. Like Big Bench is like a benchmark which can kind of like test the performance of those kind of large language models. And GPT-3 doesn't do very well in this one, but PaLM, when we scale the number of parameters of PaLM, it seems like it gets some kind of breakthrough. So this is in line with all the other kind of machine learning programs. We have seen that if you have enough data that's correct and then you scale things up, it will get very good results. So we want to take use of this kind of breakthrough in our kind of robotics problems. And another thing that is very kind of interesting is that through PaLM, we actually find that if you actually give some hints in a correct way, it can actually reason about the problems and give you some really kind of surprising results. For example, on the left side, there's like a standard prompting, and then there's like a kind of like a mathematical problem, and then if you tell it the answer is 11, and then ask it another one, it actually doesn't know the answer. It can give you like a wrong answer. But however, if you prompt it in a right way to give it some context of like some of the intermediate steps of how it come up with a final answer, the language model is actually pretty smart, and it can try to follow how to solve the first problem and give the right answer to the second problem. So that's very amazing. And we want to kind of, this is also one kind of hint of how we should do the robot learning with the language model. So let's say if we only have like language model pre-trained, we use it directly for robotics, it might probably not work very well. For example, if I say that I spilled my drink, can you help? Language model may say that you could try using a vacuum cleaner, or do you want me to find a cleaner? But however, like these tasks may not be some of the tasks that we have already trained. So robots are very kind of dumb right now. Like they only know how to solve maybe 10, 20 different tasks, but not like all the kind of task space. So I mean, the language model should actually try to choose from whatever tasks that robot can do and propose what should you do like as a first step, right? And another thing is that language model doesn't know the kind of word state or the other stuff because it doesn't have the eyes kind of like plan. So like, for example, if you're already in front of like sponge, actually the best way here is try to let the robot to pick the sponge and then try to wipe the floor instead of like try to go somewhere to find the vacuum cleaner, right? So this is the whole kind of the intuition. So how do we try to come up a way to let the language be like a smarter planner? So the idea is the following. So we can first try to just use the language model and across all different kind of tasks that the robot is already trained on and can do. And then we use the language model and try to calculate the probability of each one of them. So in this case, for example, the command is like, please put an apple on the table. And then like across all different kind of like tasks that the robot can do, the language model will think that the pick up the apple would be the most highly possible one. And this has like the highest kind of score. On the other side, we also train like a robot affordance model in a way that using reinforcement learning, for example, and it will have like a Q-learning, it's a Q-learning based method. So it will have like a Q function or value function. It will describe like how much chance it can successfully solve this task given the current image, for example. In this example, like on the right side, you see that the robot actually just parked in kind of a new environment. Like this is one of the Google micro kitchen. So it's actually not very close to the apple. So from the robotics affordance model, it will actually think that find an apple will be the most highly successful kind of task. But pick an apple will be very, very low successful rate because it doesn't even know where the apple is, right? So, and then like by combining these two kind of probabilities, you basically kind of like multiply them together, and then you will find the best one in this case, which is trying to actually find the apple first. And once you actually find the apple, right? So for example, you execute this task of find an apple, the robot will move around through the micro kitchen and it will park, hopefully it's successful, and it will park in front of a counter and it will see an apple, and then it will stop. Then it will ask the language kind of planner again of what should I do next. So at this stage, I mean, you're already in front of an apple, and then language model will think that you should pick an apple. Robotics affordance model will also think that pick an apple has a very high success rate possibility, and then it will choose to pick an apple and then execute it, and then we can go on to like pick it and then maybe bring it back, things like that. So this is like the whole basic idea for the language planner. And this is another example, like if you want, I spilled my drink, like can you help? So like the language model itself will first try to propose, find a cleaner, try to use a vacuum. But because of the affordance model we have for the robotics, and then it will try to actually find the sponge, and then it actually finds the sponge, and then you can, I mean, take it from there. Right. So the entire system look like something like the following. So you first have a language planner, which has two models. One is like the PaLM, it's a large language model. Another one is the affordance model trained on the robot by itself. And after it decided like what kind of the first task you want to do, either it will be a manipulation task or it will be a navigation task. So we will have to train separate models for manipulation primitives or like navigation primitives so that it can try to solve the underlying smaller task in a kind of successful way. This actually have a lot of advantages. If you think about it, if you have a bunch of like long range kind of long horizon tasks, it's very hard to actually train the whole system end to end. Like, for example, if I want to ask the robot to clean up my room, there might be like tons of different kind of small tasks in between. It depends on like, I mean, how messy your kind of room is. It will be very different kind of solutions. If you always collect the whole kind of trajectory, it might be very, very hard for you to actually cover the whole space. But if you can, I mean, break it down to smaller primitives, it's easier to collect the data and solve a simple task first, and then try to connect them together through the language planner. Okay, so we implement the whole system and we did some kind of evaluation. The result is actually pretty good. So if you just talk about the planning success rate is like 84%, which is something that we have never seen before. And then if you add on those kind of primitive policies, because they're also not very perfect. So adding on those permitting policies, the entire kind of execution rate is 74%, which is also pretty good, acceptable. We run over like 100 long horizon instructions and did all the comparison with other kind of variations, and the results is pretty good. So this is like a quick demo video. This is in an actual kind of Google micro kitchen. And in this case, like find cold can. Sorry, it first choose find cold can, and then it choose pick cold can. Now it choose go to the trash can. And finally it choose put down the cold can. And done. So. And then you try to pick up the sponge. And go to the table. So it's supposed to learn how to clean it by itself, but we haven't gained that ability yet. So some human try to help it. Yeah. Okay. So right now, like on the right side, you can actually see like a nice graph. So what it shows is that if we kind of keep the underlying robotics primitives models fixed, and also keep the robotics affordance model fixed, but just changing the language model from a very small size to a very large size, the actual kind of robotics planning performance is actually increasing. So this is actually the first time we have ever been able to see that the robotics performance actually scales very well with better language models. And then like, actually, question?
Yeah, no, I'm just wondering, so given that, previously that there's some small mistakes here, right? Wondering if you're using like one learning approaches to improve on mistakes like this. If you're using like Queryable Map.
Yeah, this is a very kind of interesting question. So I mean, in our team, we kind of, there are like two axes for us to kind of increase our robots kind of capability. One axis is trying to learn more and more different kind of skills. And number two is trying to polish on one specific skill. So we are working on these two threads at the same time. I would say like we focus a little bit more on the number of tasks we are trying to solve right now. So for example, if we try to do something in the micro kitchen, maybe make you a coffee, all those kind of different things, we'll try to explore that area a little bit more. So that, I mean, for example, if we can click some demo and train some models, either in the imitation learning or reinforcement learning to get like 50%, 60%, we think it's good enough. We'll try to learn some other new tasks first. And then in terms of like lifelong learning, try to polish the existing tasks to be very, very good. So there are also like a few threads people are working on that. They're using a lot of like reinforcement learning stuff, try to let the robot try to learn from its own kind of errors. So this is also something that we're working on. Yeah.
I was also curious about I saw the robot, I think it like flipped the can over at the time. So let's say it's like the can that's like half full or something. For that kind of stuff, which is like not that big of a deal, right? But it seems like it can have like a simple solution. But I'm wondering how your research team tackles problems like this. Do you think it's a better idea to follow something rule-based, where you model dynamics of things like liquids inside cans to do explicit reasoning of the dynamics of all this, so that you never throw it backwards like that? Or do you expect that to emerge? That behavior cannot have it upside down to emerge from feedback or from examples that is.
Yeah, so I think in our team, we believe that the hard-coded rules will not scale. So if you think about like self-driving, right, it's kind of like just one task, and there's so many kind of edge cases. And now if you're doing robotics, there are like thousands of millions of different tasks. It's just like impossible for you to kind of hard code. So it has to kind of learn from the data set feed by the human. It actually could be like, if you think about like if there's like an actual home robot in everybody's home, the situation is very different from each different kind of places. And it's better for the human to teach the robot in a specific way that's tailored to their kind of needs, the best for it to kind of scale. So yeah.
So the actual language primitives were just a fixed set of rules in the endpoint. Like, sorry, can you go over it?
Yeah, sure. So so we have like a list of the tasks that robot can do first. And then given those kind of lists, the language model will try to give a probability of, given the question, what's the probability of doing that task? Yeah.
And like to actually connect it to like the image
Mhm.
perception, like do you run an object vector on top of it, or like we have a representation?
Yeah, so there are multiple ways. I mean, in our specific kind of case, what we do is that we actually use a Q-learning-based method to train a reinforcement learning agent, trying to solve the task first. And then, I mean, the side product is that you have like Q function, so that given an image, you will have like a value function of how kind of likely it will going to be successful, and use that number as a property here, and use that for this. John?
When you have to like pre-specify the like task purpose, right? In this
Yes.
case, each of these like train tasks.
Mhm.
I guess my first question is, how easy is it to add? It's just a matter of like kind of now you have like +1. And I'm assuming that when you get like these probabilities, it's just like what, querying the model for like a search type of thing, or
I think there's a specific API you can call to get that probability. Yep. And then like in terms of like adding a new task, for the language model is, I mean, we didn't actually train the language model. We're just using the language model, pick it out, and then do some inference. So I mean, the language model is fixed. So adding a task for the language model is nothing. But adding a task for the manipulation primitive is like a total kind of new area, depending on how difficult the task is and how similar the new task is to the previous task. For example, we know a lot of like pick tasks. We can pick an apple, we can pick a bottle, we can pick those kind of different kind of weird stuff. And if you want to add another pick task, it might be easy. But if you want it to do some kind of upright code, it might be very hard. So depending on like what kind of new task you want to learn, and we're trying to also figure out like what's the best way to acquire new tasks in our team.
And it's like my second follow-up, kind of already.
Yeah.
So are each of these tasks like individual policies, or like
It's one single policy. So we have like primitive policy, which will take language command and the image as input and output an action. So yeah.
And then I guess like the last part of this is do you like kind of expect like generalization? Like I know like the BCC paper does like pick up object and just like kind of swap things and kind of set. Do you observe like the similar trends?
Yeah, we do expect that. So for example, initially I mentioned about the compositional stuff for the language model. So it's also like if you learn like pick an apple and you learn move an orange near a bottle, we would expect it to also learn pick a bottle, something like that. So yeah.
Thank you.
The model like somehow on the specific set of tasks, or is it just methods?
You can fine tune; it will get better results. But even if you just use SES, it can already give some like reasonable results. So okay, so I think yeah, I think that's pretty much it on my side. Like just to summarize, like by basically combining the language model and the robot affordance, we can build a language planner to kind of divide the long range tasks into smaller primitives, and then we can solve it individually with the manipulation policy or like navigation policy. And we also find that like planning performance can actually scale with an improvement language model only, which is quite kind of surprising. So next, I will hand it over to Keerthana again to talk about some of the follow-up work in our team.
Right. So as Yao pointed out, what PalmSecan does is it does open loop planning. So the language model generates a plan, and then the manipulation primitive executes that plan step by step. However, there is a lot of information in the data that we are still not feeding the language model. So first is the concept of world states and robot states. So our robot is looking at camera images only. So world states means the information inside the image and what the surroundings look like. And now you can describe that surroundings in natural language as apple in drawer or orange in drawer or Coke in fridge, which is basically denoting what are the objects or what objects are there and where they are and what locations exist. There's also robot states. Naturally, in traditional robotics, robot states are sort of described as like motor commands. So like, let me finish this. So like torques and angles and stuff. However, you can also describe the robot state in natural language, like for example, banana in gripper or near the cabinet. And so you can use this information and feed it into the language model. Yes, go ahead. Mhm.
Is it like currently like basically that or is it also like
Yeah, that's a very good question. So that is the primer for the next slide. So this is work from our colleagues called Inner Monologue. And here the effort is to close the loop on planning. And how are we doing that? So information in the scene. For example, you can do object detection using another model, and then detect all the objects, and then you can feed that information back to the language model. So what objects are there is one kind of feedback. A second kind of feedback is success detection. So you can use like a clip or other visual language model to ask, did the task succeed or not, based on like multiple states. And you can also feed the success detection information to the robot. Why this is useful is like, for example, you say, the robot says, I'm going to go pick up a Coke can and then do something with it. However, you failed in picking up the Coke can, and then it is kind of infeasible to then continue along the next steps as if nothing happened. So you need to replan based on the contingencies and based on your success or failure rate. A third kind of way in which feedback can be fed to the language model is interactive. So we have a chatbot interface where the human is interacting with the robot in the video that Yao showed. So for example, here a human says, bring me a drink from the table. So the robot goes to the table, and then the robot, the scene descriptor says, I see a Coke and lime soda from the object detection. And then the robot says, what drink would you like? And the human says something with caffeine. Then the robot goes and picks up Coke, and then let's say it fails, and then the robot tries again, and then so on. So using this feedback, like using human feedback, helps the robot interactively plan alongside the human who gave the instruction in the first place. So here's a video of Inner Monologue. So the language model is working. Now my colleague is trying to disrupt. Action was not successful. And the robot has to replan. And then robot brings the lime soda. So this is an example where, because you close the loop, you can interactively replan based on contingencies, based on what is in the scene, based on feedback. Right. Now there is another set of information that we are leaving in the scene. So PubSecN, as it was published, uses hard-coded object locations to navigate to objects. So for example, when I say, find me a Coke can, you have to feed in where exactly the Coke can is in the room in order for it to go to the Coke can. But this means that you're fairly limited in your knowledge, and you have to sort of pre-process your scene. You have to, like, a human has to send it where the objects are. but this can be automated very easily. So the next work is in attempts to do that. So the idea here is that we built a map of the scene, and that map is queryable through natural language. Again, we are using language as an interface to create a map. So the idea here is that the robot first goes around and then does a scene exploration. Then we collect a bunch of images of like what is where, and we also know like where I took that image. After that, you run like a object detection network on it, and then you get all these object detectors. Like for example, there's Coke can, there is like a danger sign, there's a plant. And then what you do is we use like a visual language model to build like a queryable representation of the scene itself. So for example, once you ask like, where is the trash can? And then it tells you like where the trash can is based on the relationship between the word trash can and the image of the trash can. So you know where the trash can is, you know Coke, and you know where the plant. So Cliff and Wilt were used in this work to build the map. So the idea here is that we are basically using VLM to encode information about the world, and then using that to inform the policy in order to generate actions. So this is an example of like how it would go. For example, let's say the instruction is recycle the Coke can, and the object proposal says I have a Coke can and I have a recycle. So the relevant objects are Coke can and recycle bin. Now, you have already explored the scene, and then you query the context with it. And then it tells you that Coke can is at x1, y1, and recycle bin is at x2, y2. Then you generate executable options. So what you do, like as Yao described with Palm Say can, you go to the Coke can, but now you know the exact location, and this is automated to a certain degree. And then you do pick up Coke can, put down Coke can near the recycle bin. So this is highly context-aware planning, and is part of using closing the loop and using language model to make the planner more flexible. This is extremely important when you use, like, if you want to deploy in like a home or office environment, everybody's homes or everybody's offices are structured differently. Objects are like the distribution of objects are very different. So in order to build a robot algorithm that is that can act in these environments, you need to be extremely generalizable and extremely flexible. So here's an example of NL map in action. So the robot picks up the chip bag. And then it goes to the bin by itself, and then it drops it. Not very successfully dropping, but will do. All right. So now, again, this gentleman here asked the question of like safety, right? Like, should a robot be throwing a Coke can with like half Coke in it and damaging things? No. But would machine learning by itself, like you can use data to learn that you should not do that, but you cannot guarantee that it will not do that. So our approach to safety requires multiple layers. So we have, of course, we have machine learning based safety, which is like trying to never land in a place where you can take a bad action. However, we also have like unfailable safety standard, like collision avoidance, or e-stop, where the operator can intervene and then stop the robot. The next, another feature or safety feature of our system is interpretability. For example, here, if you look at it, in this particular example, there is the language model which is generating all these plans, and then there is the affordance model which is rating these plans. So you can see the scores of the language models, you can see the scores of the affordance model, and you can also see the final final score of the output. So it's very useful for debugging. It's not like a black box. Like individually they are, but their interface is very interpretable, and their interface is also in natural language. So it like any human can look at it and then understand what is going on. And also these two are sort of contrarian to each other. The language model is grounded by the affordance model, and language model can suggest a lot of things, and the affordance model is what restricts it to only like a safe set of actions that it can do. However, yeah, go ahead.
Question about like you. So yeah, like in a hypothetical situation where you're saying like I'm deploying this robot in the environment. If I'm trying, let's just say like a robot doesn't understand like what cocaine is, right? It's not in vocabulary, but I deploy into an environment where it has to learn. Is it possible for the robot to learn, like basically is it possible for the robot through interaction with the environment learn to like adapt with language and stuff to what you think?
So yeah, but usually the visual language models are trained on a large data set, right? Like for example, Clip. So it already has a lot of understanding of the world. Now, potentially what you could do if you want that is like fine tuning them to like understand new things. Like for example, I think one example could be like, let's say people, right? Like semantically notating like who's my mom or my dad. Now that is something that Clip would not know, but if it's operating the home environment, I can show it, and then eventually it knows.
I guess all of that is I think like most of this is basically like coupled down by like I guess like the implication also in the previous section that your planning is like up or down by like complexity of your thing that guys will be planning things like that. But is there a way maybe like to me it seems like there's like it's like two games, right? You have like one, you know, like one person that's going against the other, right? Like, is there a way so that like you're not up or down by either? Like that one improves the other, and then the other one improves the other module that you put back and forth. Because I think like kind of what you're saying here is that you have so much information in your environment, there's so much possibility. Like, is there a way that you can break through that?
You potentially can, right? But the question is like, should you? Like language models at the moment, it's generative, so it can say a lot of things. Like, is it actually safe to do that? If imagine if they were training each other, and then it could also like digress, right? So the idea is to like maintain the right balance, and I think this setup makes sure they are acting with real world information rather than going off on their own tangents. There was a question over there.
Yeah. Another question. Do you know like the ability? So like, let's say I want a specific item that's maybe across from another item, right? Or in like a single frame. Like I want the object A that's like next to object B or across object C, or like I specify some other command that defines one instance of what might be multiple objects. Do you have a way for handling that kind of situation, or does NL Map already handle that?
Right. So one idea is that so NL Map is already not looking at one image. Before building the map, you actually query the entire scene. So a robot just like exhaustively goes around and then clicks a picture of like everywhere. So then you know where the locations are. However, between multiple images, right now it's not 3D, so it cannot reason that this Coke, like if you tell it Coke can, let's say there's a Coke can on this table, and then there is a Pepsi can across it, and then if you say bring me the drink across from the Coke can, that would be harder for the visual reasoning to reason about because it's not 3D, but that could be improved upon. But for 2D things, it should work. Yeah. So despite the safety features, there are still a bunch of failure cases. So one common mode of failure is the LLM error. So when the LLM does not propose the right plan, then the robot cannot do anything, like the affordance model cannot do anything. So like if you played around with GPT-3, one of the failure modes you would see is that it just like goes in a loop. It like keeps completing itself. And then, so here in this case, it's like, can you bring me a bag of chips from the close counter, and then it says, go to the close counter, go to the far counter, go to the close counter, go to the far counter. So this is a failure mode. A second failure mode is like early stopping. So this is where like you give a long horizon instruction to the robot. However, it terminates the episode fast. So let's say you bring me a lime soda and a bag of chips. The robot brings a lime soda and then terminates, but it should actually continue and bring the bag of chips as well. Third failure mode is affordance misclassification. Uh, like Yao said, the affordance model is basically modeling the probability of success of a task should I attempt it in this state. Now, that estimation of that success is also learned because it's coming from a reinforcement learning like Q function. So if that is wrong, then I could attempt a task or I could score a task as high, which I'm not very capable of doing, and then ultimately my sequence fails because I did not succeed at that task. So in this case, for example, how would you bring me something to clean the kitchen with? I would find a sponge. Now the next thing is put down the sponge, but we're not very good at it, so then it like fails on that. The affordance is wrong, so it actually like picked the wrong thing. Now, like despite the failure cases of PalmSecan, if you look at it, most of our tasks, as John pointed out, are very limited by the amount of things that the underlying manipulation primitive can do, like the amount of primitives the manipulation model can do. For example, if you do like pick tasks, then you pick and place tasks, you cover a large range, but in a home environment, you still have a ton of new skills to learn, a ton of new states. Like there is a lot of visual reasoning in manipulation itself that needs to be handled, and that is very separate from planning. So this is a very hard thing, and then you need to collect data for it. It's very engineering and ops heavy. It's very costly because we are training these manipulation primitives in a supervised fashion. So there's some human effort involved in gathering these data set. Yeah, and so that brings to the second challenge, which is how to generate useful data and how to do that in a more automated fashion. Imagine if the robots themselves can figure out where or like what skills to practice, what skills it doesn't have knowledge about, and then it can like go and collect data on them. And the third challenge is, let's say, despite now you collect data on multiple tasks and you are fairly general and you collect them in like various kitchens, how do you construct a manipulation architecture that can scale with these skills? So often you see a lot of catastrophic forgetting in multitask models where it can do some things, but then it's not very good at modeling the whole distribution. And these are some of the things that we are working on. So you should look out for new releases from our team, and we would have something very soon addressing these like manipulation challenges. Thank you for being here, especially in the evening, and giving us your time and for listening to us. I'm Keerthana, and this is Yao. And this is our email addresses. Feel free to contact us. We're also on Twitter. Yeah, thank you for the opportunity to interact with you guys. Yeah, question.
So first, the robot goes around the scene and then what if I want to know what like generalize the style what's neat, you know?
Yeah, so the exploration is exhaustive and it was done initially. So yeah, it's not very dynamic to object locations, but potentially you could also update it. If I notice a change while the task is being done, then I can update it. But then if I never, let's say I first scan the place and then now I'm in this room and then somebody moved an object in the other room, yeah, I would not know, and I would think that the object is still there. So I think we need more failure management to like go to handle that kind of scenario where there is like movement of objects themselves.
Where the robot goes, if it sees the same object move to different belongings path, Okay. So how does it differentiate, know that that's a different object? That's the same object. That's equal, like,
Yeah, that's true. It does not reason in time, so then it would not know that it is actually, it would think that it is a different object because it doesn't move in time.
It depends on like whether you go back to the original data. So if you have everything there, maybe it's a new object or like if you are really well, but if you go back to the original place up there, then you can say that it's a telephone. It's something like what human do, right? So yeah, if you're human, like you also trying to do those things. So we actually don't have that stuff implemented, but it's something like good idea for us.
Yes.
Is good strength and good as people who have myself.
Can you repeat that?
Good strength. So I
Right. Is that something we train on? Yeah, we do. So that is the manipulation primitive. So pick cocan, pick apple, like there are different grasps. There is different amounts of fragility of objects, small objects, like for example, of picking up a fork is actually quite hard when you have only 2 fingers. Yeah. Yes.
Let's talk architecture first. We've always gone through this thing, just like, so I'd imagine that some policies, like learning policies, like the current policy of Reddit, like a policy that just informs voters. Is it necessary to disentangle public policy reform with the intention of like that? Does that make sense? It's like let's say you have like an option to like pick up the code can, which is like the correctly realize since but the policy sucks. Is there like any way to address that? Does that make sense?
Yeah, it does. So yeah, like I said, affordance failure is one failure mode, affordance misclassification. So here you think you can pick up the cocan, but you're actually very bad at it, but then you still attempt it. So to some extent, inner monologue can handle that failure. So you fail at it, and then let's say you fail at it 3 times, then you need to replan. So then maybe the language model comes up with a new plan. Yeah.
It's like, is this trained on sim or?
No, this is all real.
So then the affordance is actually to try something. So there are like multiple ways to get the iron to work. You can train on the real data directly. You also can set up some sim environment for data systems. That in the paper that we published is actually a simulation first sim to real model translation. So we also have like a real data only kind of to them. There are different approaches and depending on which one works best with this work. So
Thank you.
Yeah. Go ahead, one of you.
Well, okay. So given how a little bit of a simple question, but given how fast you guys are able to get this after LLM started going crazy and stuff, how many more years do you think it'll take for us to get household robots that we can just use?
That is a very hard question, and it is above my pay range. This is research at this point. So this, like, our capability.
You can first ask like how many years will it take for us to get autonomous driving, and then we can.
Yeah, exactly.
That's like one task we are solving for different kind of tasks.
So I guess maybe it's a funny question. Like, so imagine like I don't know. I guess like it's like 10 years. I think you guys are very smart. So let's just say 15 years. We solve this. What do you think is going to be, at least from how we can understand the problem, right? How we think is the hardest step along that path? I think it's like the dexterity of the task. Do you think maybe it is the planning or the what is the hardest step that we build?
I think data is like getting the right kind of data. Let's just take home and office robotics, for example, office environments. So here, everybody's offices look different. There's a lot of lighting conditions. There's a lot of different types of objects themselves. There's a lot of different grasp positions. So there are many different failure modes there. And collecting, like, if you're just using an end-to-end learning-based approach, then collecting all that data is quite hard. So I think that would be, and if you look at how in language modeling it worked, like initially they were doing supervised learning. They were collecting they were gathering their data sets and labeling things very nicely. But then eventually they saw the uptick when they switched to weekly supervised learning, like how Clip is, which is not like ImageNet, where it is like labeled, but it is taken from the internet. So I think we will need a way to like map the embodiment and then sort of take leverage of free data in the world. Potentially. Yeah, to be able to train from the internet is impressive, and we need to get there. Yes.
This is wondering, like, when were there any sensors or was it just purely-
There is like it has depth. So like in the NL map SECAN, in order to actually go to the object, you need depth.
I would say, for example, the take passes to train on. Also, another factor that we want to put in the ball.
Yeah, so I'm assuming eventually there's probably down the line that are probably the goal to have more complex tasks to be tackled, like say, vacuum staircase, build staircase, which is probably not possible with the real world. So let's say the extent to like a different robot morphology. You intend to extend the same policies and try to distill that so that you can actually apply to different forms of robots, if we plan to actually train different forms of robot. I guess I'm wondering if you can abstract away the structure of the robot from
Do you want to answer the question, yeah?
I think, yeah, that's a good question. I think there are a lot of research which is trying to find it down those kind of things. For example, you want to take the data from another robot like here, and then like you want to train on it. But I think this is a very kind of like trying to get to that. We don't have like answer right now, but we're also whether this is even possible or not.
Yeah.
Yeah.
Let's say you have like an ambiguous prompt, like in the microcontroller, there might be many months, and you say, bring me a month. Is it straightforward to have the language model realize or in conjunction with the map of their diagram for view and ask the user for more questions?
Yeah, that was shown in the inner monologue, right? Where with the interaction thing, where the user can also the model can go and then look at all the monks and then also kind of ask like which one.
And so I noticed that the videos were sped up, which is pretty standard. Is that a hardware bottleneck or is there also software bottleneck?
Both. So language models are huge. So there is inference bottlenecks there. In order for robotics to work, we need to be quite fast and reactive in real time. Also, the models on the robot themselves, the manipulation models are also, they need to get bigger to absorb more data, but then you can't have slow inference. So there are hardware and software problems, mostly software like machine learning related problems. Also, we need to match the collection frequency and the inference frequency. This is the fact that our robots are slow is a problem, and we are working to fix that. Yeah. Yes. Am I allowed to say that?
It's actually not important.
Yeah.
It's not important.
Standard GPU. Yeah.
Is that a robotic updated at a or is it like
Can you repeat?
Oh, so like is it like so let's say like as a robot is uniquely dependent can we plan update over time or is it just frequently?
So for the SECAN, initially it was only pre-computed at the beginning, and then it continues the plan as is, irrespective of failure or like things moving. But once you close the loop, then you start replanning. Yes.
I don't know what you said then. So I guess part of the part that scale is not always the models, but does that imply that you think models? I guess it goes along with what Tisha's trying to say is like, do you think that like models? Do you think it's mostly like an engineering problem to get models to run faster, or do you think there's like some like very necessary need to still either distill models or break up models or have an expert?
You should look forward to our new work. I think we tackled some of these problems, like how to speed up inference. I think a lot of work needs to be done on this front. There's a line of work which is like trying to make transformer inference faster. Also, like let's say if you want to run it on a mobile device and stuff, Google has a lot of work. Like there's performers, there's token learners. So yeah, we also have some work you will see next week or in the upcoming weeks, and it's an important problem to solve, and we're just beginning to crack at it. Yeah.
I think it's very back to like John's question about like how hard is it try to learn new task, and do you like per task per model, or like you want to use like one single model to learn all those different tasks given the language instruction? I think that is really hard if you want to really scale it up for the underlying kind of manipulation parameter model. So if we can do like 100 tasks with one model, but if you want to scale to 1,000 or like even 1 million, that will be a very kind of difficult question you are trying to tackle.
It's like a conflicts.
Yeah, yeah. Yeah, you have to scale something up. Another constraint for robotics is like the inference needs to be fast. So you cannot just make the model bigger. You have to come up with something smarter. So yeah. Yeah, exactly.
Yeah. Also, like distillation for each skill would not scale if for like let's say if you have 1 million skills. Yeah.
This is not a hardware question, but what is that? What kind of sensor is spinning thing?
It's a LiDAR.
Just a LiDAR.
All right.
One more round of applause.